Okay, so now that you have learned about precipitation reactions and how when you mix some chemicals together they will make a reaction, and when you mix other chemicals together it will be no reaction. Well, now we have to learn that, or we get to learn, that there are different ways that we can actually write out those chemical equations. So there's molecular equations, there's complete ionic equations, and there's net ionic equations. So basically it's three different ways that you can write an equation for the same reaction. Yay! All right, so let's start off with molecular equation. So a molecular equation is an equation showing the complete neutral formulas for every compound in the reaction. Okay, so here is a molecular equation. Silver nitrate plus sodium chloride reacts to form silver chloride and sodium nitrate. So everything is there. It's the complete neutral formulas. There's no ions shown. We have all the symbols. Bam. That's a molecular equation. That's what you're used to. That's what we just, practiced the first half of the lecture. Okay, so this is what you're used to. Now, we can also show this same exact equation, but using the ionic symbols. So, here, see, oh, yikes. See how we have aqueous, aqueous. What does aqueous mean? It means that it's dissolved in water. It's ions in water. So, we could show this same equation written out in all of the ions. So anytime we have an aqueous, an AQ compound, we would write it out as the ions. So sodium nitrate would be silver. Silver nitrate would be the silver ion written out, the nitrate ion written out. Okay, so Ag plus, aqueous, NO3 minus, aqueous. Okay, and because sodium chloride is aqueous, all right, we would also write him out as Na plus for the sodium ion and Cl minus for the chloride ion. Okay, now on the other side of the equation we have aqueous over here, so we would write sodium ion aqueous and the nitrate ion aqueous. The only place we do not have an aqueous is right here, this solid. So we cannot write that out as ions because they actually find each other, they're attracted to each other, and they hold tight, okay, as a solid substance. So we would have to leave that one as AgCl because that one is not aqueous. It is not just free-floating ions in a solution. It is a solid that forms when this chemical reaction takes place. So this is what we call a complete ionic equation. Dun, 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 dun. See, right here. Complete ionic equation shows the reactants and products as they are actually present in the solution. Okay, because remember, aqueous means that they are free-floating ions. So we have, since both of the reactants were aqueous, we have Ag plus aqueous plus NO3 aqueous, and we have sodium aqueous, and we have chlorine ions aqueous, reacting to form. Okay, here's our solid. We cannot write that as ions because that's actually solid. They're not free floating anymore. They've found each other. Okay, and they're holding tight. Okay, but the sodium and the nitrate are still aqueous. Okay. All right, so what happens, okay, is that we see a lot of the same ions before and after the reaction arrow, right? So we see the same ions, okay, we see the same ions NO3 on both before the arrow and after the arrow. And we see sodium before the arrow and after the arrow. So basically that just means they're just hanging out there the whole time. They're what we call spectator ions. They don't do anything. All right, they're just hanging out going, yep, I'm still not attracted to you. Yep, still not attracted to you. All right, so they're spectator ions. They have no place in the chemical reaction. They don't matter, actually, in essence. So we can simplify this equation to get rid of these spectator ions that just sit there and do nothing. And we can just show the ions that actually find each other to do something. And which ones would those be? You guessed it. The Ag and the Cl. Those are the ones that we actually care about, because those are the ones that get together to form AgCl, which is our solid. All right, so those are the only ones we care about. So we can simplify this equation to get rid of these spectator ions. And when we do that, it looks so much neater. Okay, so this is what we call the net ionic equation. Okay, net means when you get rid of all the extraneous things that don't matter in a chemical reaction, because they just sit there as ions anyways. All right, when we get rid of all those other ones, we get down to the meat and potatoes of what's actually going on in this chemical reaction. The silver ion and the chlorine ion hook up to make silver chloride. Bam, that's all we need to know. Everything else is just junk. Okay, so a net ionic equation shows only the species that actually participate in the reaction, and that's all we care about. Okay, so that's what we call a net ionic equation. All right, so we've got molecular molecular equations that show just the neutral formulas. We can have complete ionic equations that show all of the ions that are involved in the reaction, and then we can get rid of those stupid spectator ones that don't do anything, and we can just show what's called a net ionic equation. All right, which actually shows what is actually going on that we actually care about, actually. Okay? All right, so let's take a look at one more example. Here we have hydrochloric acid, aqueous, dissolved in water, okay, and sodium hydroxide dissolved in water. Here's our little reaction arrow. And this reacts to form H2O liquid. All right, so pure H2O. Okay, so this guy here is not aqueous. Okay, seems kind of strange because it is water, and stuff dissolved in water is usually aqueous, but this is actually pure water, so that is not AQ. All right, so that means a reaction actually occurs. Okay, so we cannot just write, no reaction for this, because, we can't actually see what's going on because there's no precipitate cloudiness. All right, but anytime water is actually formed in its liquid state, pure liquid state, a reaction has occurred. We've gotten water back. Okay, so please keep that in mind. All right, so here's our molecular equation. HCl plus NaOH reacts to form H2O and NaCl. All right, NaCl, again, if we look at our solubility chart, is going to be aqueous, and so that's no fun for us because we can't see that. All right, so because we have a bunch of aqueous symbols here, again, we can write it out as our complete ionic equation. So we can break up the H and the Cl and put H plus and Cl minus. We can break up NaOH. And we have Na, and remember OH is a polyatomic ion, so it has to stay together. Polyatomic ion. All right, so it has to stay together, so OH sticks together. It's a negative charge. Right, and then here's our reaction arrow. H2O liquid, okay, we cannot break those apart. Remember, it doesn't mean aqueous. So H2O stays together. But then we've got NaCl aqueous, so we can break those guys apart into Na and Cl. Okay, so again, we've got a bunch of what we call spectator ions, ions that occur before the reaction arrow and after the reaction arrow. They're the same ones. So, for example, sodium and sodium. Chlorines before and chlorines after, right? And so those are our spectator ions that don't do anything, and so we don't care about them, and so we're just going to kick them out. All right, and so the ones that we actually care about are the hydrogen ion and the hydroxide ion that come together to form water. That is our reaction. And so that is what we're going to write down as our net ionic equation. H plus and OH minus react to form H2O. Bam! Just like that. All right, so here's some time for you guys to again pause the video, and write out the complete ionic equations and the net ionic equations for these two reactions. Then you can come back to the video and see if you did it right. So go ahead and pause it. And welcome back. Let's take a look and write out these complete ionic and net ionic equations. Okay, first one. Lead nitrate and lithium chloride react to form lead chloride and lithium nitrate. Okay, and we can see here that we've got a solid. All right, so that means a reaction does occur. It's not a no reaction. So we can write the complete ionic and net ionic equations for these. So for the complete ionic equation, we are going to look at all of these lovely AQ symbols and write out the ions that make them up. So we are going to write out Pb plus 2, aqueous, and we're going to write out NO3 minus, aqueous. All right, and lithium chloride is also aqueous, so this 2 is going to distribute to both of them. So we're going to write 2 Li plus and 2 Cl minus, and I'm going to run out of room, so I'm not going to write the aqueous little symbols anymore, but you get the idea. Okay, and on the right-hand side, PbCl2 is a solid, so we cannot break him apart. So he's going to stay together. All right, but we do have another aqueous, Li and NO3. Those guys are ions in the aqueous form. Okay, so that's our complete ionic equation where we break up all the AQs into the ions that form it. Now the net ionic equation, we are going to get rid of the spectator ions, the ions that are present before and after the reaction. So let's just look, we always look at the end of the reaction, okay, and then see if we can match up ones from the beginning. So lithium is a ion in the end, and so we'll cross him out, okay, from the beginning. And nitrate is another ion that's still sticking around, so we're going to knock him off from the beginning as well. And so what we're left with, if we cross all of those guys out, is we're left with our complete ionic equation, which is just Pb, so Pb aqueous, plus 2 chlorine ions react to form PbCl2, that is a solid. Dun, dun, dun. And there you go. That is our net ionic equation. We've gotten rid of those spectator ions, the ones that do nothing, and that's what we have left, the actual reaction. All right, okay, last one, let's take a look at the reaction between hydrobromic acid and calcium hydroxide. Okay, so this is our molecular equation all spelled out for us, and we need to write down the complete ionic equation first. So again, we're going to convert all these AQs into their corresponding ions, and we will make sure that whatever coefficient is out in front also gets out in front of each of the ions. So 2H plus 2Br minus. Then we have a Ca, and calcium is a positive 2, and an OH. And there's 2 of those because we have a 2 right here. All right, and then on the other side of our equation we have the L. All right, so that means a pure substance. So that means a reaction has occurred. There's no ions there, so we have to leave those intact. Okay, have to leave those intact. All right, but over here, there's an aqueous, so we can split those guys up. Ca plus 2, and Br minus, the 2 out front. All right, so next we have to put those spectator ions on the chopping block. So again, look at the products first, okay, and then see if they've got corresponding ones on the reactant side. They always will. All right, so bromine is on the chopping block. He's there before and after. Calcium's on the chopping block. He is there before and after. And so what are we left with? We're left with 2 hydrogen ions in the aqueous form. We're left with 2 hydroxide ion molecules, and they are going to come together to make water in the pure liquid form. Bam! There is our net ionic equation. Beautiful, I know. All right, so all of that had to do with precipitation reactions, so knowing the solubility rules and figuring out if a precipitate's going to form, and then knowing how to write the molecular, complete ionic, and net ionic equations for each. So that was kind of a big chunk of our lecture today. So let's look at some other types of chemical reactions, like acid-base and gas evolution reactions. So acid-base reactions form water upon mixing of an acid and a base. Okay, so remember, an acid is a compound characterized by sour taste, the ability to dissolve some metals, and tendency to form H+ ions in solution. Remember, acids will always have their H out front in their chemical reaction, like HCl or H2SO4. Okay, that H out front is our ionizable H, means it breaks off to form an H+ ion. Bases are compounds that are characterized by bitter taste, slippery feels, and the tendency to form OH ions in solution. Bases typically, but not always, have their OH in the back of their formulas, like CaOH, NaOH. See, they've got the OH there, but not all the time. Sometimes they are bases because they take an H from water to leave an OH behind, but we'll get there. Okay, so here is an equation, an acid-base equation. Hydrochloric acid plus sodium hydroxide react to form water. So here is our key, right? Acid-base reactions form water upon mixing of an acid and a base. Okay, so basically this is also called a neutralization reaction because we're neutralizing the acid and base by making water, which is a neutral substance. So if you have an acid spill, one way to get rid of it is to neutralize it with a base, or if you have a base spill, you can neutralize it with an acid. All right, so let's take a look at the. In fact, here we go. Acid-base reactions are also called neutralization reactions, generally forming water and an ionic compound called a salt that usually remains dissolved in the solution. So we can see here that we've got our acid, H2SO4, sulfuric acid, and our base, which is potassium hydroxide, reacting to form water, H2O, and our salt. A salt just means an ionic compound. Ionic compound is also called a salt. Not all salt is table salt, okay, which is the salt we use to season our meat, our food with. Salts could be any ionic compound. So in this case, we have K2SO4, potassium sulfate. All right, and we can see that the salts are always going to be found dissolved in solution. So the salts will always be aqueous. So that's our pattern here for acid-base reactions. Acid plus base equals water and dissolved salt. Bam. So you try it. Write the molecular and net ionic equation for the reaction between aqueous nitric acid and aqueous calcium hydroxide. All right, so again, take a minute to pause the video, discuss with your peeps, and then come back to see if you are right. All right, so molecular equation is just our chemical formulas. So we're going to start off with what we're given, HNO3, and then we say that's aqueous, plus CaOH2, and that is also aqueous. And since this is an acid and a base, we always know that we're going to have water, H2O, and here's where it comes from. It's just like a double replacement reaction. H is going to drop the NO3 to hook up with OH, and HOH is H2O. Okay, so there's where our water comes from. And to figure out our dissolved salt, we take a look at calcium. He's going to drop hydroxide and hook up with NO3 now. So we're going to have CaNO3. And that guy is going to stay aqueous. Okay, so there is our molecular equation. All right, and oh, you know what, let's put an L here to make sure we know that it is pure water. All right, and so what we need to do is also the net ionic equation. And remember, net ionic equation just shows us what we, which parts are actually involved in the chemical reaction, not just spectator ions. So here's a little trick. Whenever you're doing net ionic equations, look for the product on the right-hand side that either has an L or an S. In this case, water is our L. Okay, that's going to be our product, right? And which ions have to make H2O? Well, my dear, H plus and OH minus. Bam, H2O. There you go. There's our net ionic equation. So if you can just identify the solid or pure liquid in the right-hand side and break it apart into ions on the left-hand side, write those out, you got the net ionic equation without going through the hassle of doing the complete ionic equation. However, if the complete ionic equation step helps, please do that, whatever makes most sense to you. All right, so gas evolution reactions are ones that evolve gas. Not like evolution like gases come from monkeys, but evolution meaning that they release gas. So we're going to get gas bubbles formed in these types of reactions. So you'll see little bubbles in your test tubes or in your little wells, and that'll be a evidence of chemical reaction. All right, so here is an example. We have sulfuric acid and lithium sulfide react to form H2S, which is a gas, okay, and lithium sulfate, which is an aqueous solution. Okay, so again, figure out how they switch up. Okay, so this is double replacement again. So H is going to drop SO4 and hook up with S. Li is going to drop S and hook up with SO4. We have to always look to see on our solubility chart if anything is going to be a solid. Okay, in this case, this is sulfates, and sulfates are soluble if they're hooked up with a alkaline metal, which lithium is. So this guy is aqueous. And H2S is a gas, and there's not really a good trick to it. You just have to kind of see it or be told, like in the reaction, that it's a gas evolution. And then you can, kind of figure it out. I think in the chart in the back of your lab manual, it might actually say G for gas, but I don't remember. All right. Other gas evolution reactions aren't this simple. They form intermediate products, which then decompose into gas. So, like this one, which is hydrochloric acid with sodium carbonate, actually sodium bicarbonate, they call it. And that is going to, again, we're going to see that there's going to be a switcheroo. We're going to have sodium chloride. All right, sodium dropping HCO3 to hook up with chlorine, and then the H going with the HCO3 to make H2CO3. But this is our intermediate. This guy is unstable. H2CO3 is unstable. And so what happens is that it basically breaks apart into water and carbon dioxide. And carbon dioxide is our gas here. Okay, so a lot of the carbonates and sulfates are going to be intermediates for a lot of gas evolution reactions. All right, so kind of look for if something is a carbonate, has a carbonate in it, or a sulfate. Okay, actually bicarbonate or bisulfate. Usually they're going to have an intermediate step kind of there, an intermediate product that will decompose into some kind of gas and water. All right, so here is kind of another chart to help you figure out if there's going to be an intermediate product involved with this gas evolution reaction. So, for example, sulfides. Now that's just regular S, right? S hooked up with something. There's no intermediate. Okay, the gas formed is always going to be H2S. Okay, always, if there's a gas formed from it. Now, carbonates and bicarbonates, again, like I said, we're going to have an intermediate product that then forms the gas CO2. Sulfites and sulfites and bisulfites are going to have an intermediate product of H2SO3, and then they're always going to form sulfur dioxide gas. Okay. And then last but not least, ammonium, all right, which isn't one we usually see. Ammonium is usually going to have an intermediate of ammonia hydroxide, which is going to fall apart and basically form water and the ammonia gas, NH3. Okay, so again, this is something that you will have on tests and quizzes, so you don't need to necessarily memorize it, but just know that it occurs, and if anytime you see any of these guys here, you recognize that they are intermediate products and you're not done with your chemical reaction yet, you actually need to go that one step further and say what gas will actually be made in the end. So here's an example. Hydrochloric acid and sodium bisulfite, okay, reacts to form, again, H2SO3 and NaCl, right, by double replacement. And so remember that H2SO3 is an intermediate. It's going to fall apart into water and sulfur dioxide gas. Okay, so in the end, you have three products: water, sulfur dioxide gas, and the sodium chloride that was made in that second step. All right, so here's a you try it. So go ahead and pause and try to write the molecular equation for the gas evolution reaction that occurs when you mix aqueous nitric acid and aqueous sodium carbonate. All right, so let's see if you did it correctly. Aqueous nitric acid, HNO3. Aqueous means that's AQ. And aqueous sodium carbonate, Na2CO3, because CO3 is a -2 charge. And that's aqueous as well. And that is going to react to form HCO3 plus NaNO3. All right, and remember that this guy is an intermediate product. So we're going to have H2O plus CO2 plus NaNO3 in the end. All right, so this guy is an L, this guy's the G, and this guy is a Q because of our solubility rules. Dun, dun, dun. All right, there you go. All right, we're almost done, guys. I promise. There's only 4 more slides. We can do this. Okay, oxidation reduction reactions. or another way we call this is redox reactions, like redox reactions. Oxidation reduction reactions involve the transfer of electrons. So rusting of iron, bleaching your hair, production of electricity in batteries, all of those, you're transferring electrons to make a new product. So some involve the reaction of a substance with oxygen. So sometimes it's oxygen that's either gaining or losing electrons. So here we've got the reaction, combustion basically, of hydrogen gas and oxygen gas to make water in the gas vapor. And so this is the reaction that powers space shuttles. Wow, over there. And here is another one where oxygen is involved with a chemical reaction of iron, and this is rusting of iron. So iron plus oxygen makes iron oxide. All right, so we can see rusting right there. All right, so these are examples of redox reactions or oxidation reduction reactions, and we're going to go more in depth with them, but near like the end of the semester. All right, some oxidation reduction reactions do not involve oxygen. So if you don't see oxygen, but it doesn't fall under any other category, then consider maybe looking at it through the scope of oxidation reduction reaction and see if it works. So usually if oxygen is not involved, then we have a metal reacting with a nonmetal to make some kind of product. So basically all metal nonmetals hooking up are called oxidation reduction reactions. You never know that before. We didn't throw that at you in regular chemistry because we didn't want to confuse you yet again or any more than regular chemistry was already confusing. So anyways, anytime you hook up a metal with a nonmetal on your periodic table, you're doing an oxidation reduction reaction. Okay, because you're exchanging or transferring electrons, which is exactly what the definition we saw on the last slide was of an oxidation reduction reaction. So oxidation means you're losing electrons. So metals are always losing electrons, so they go through oxidation. And reduction means that you gain electrons. So like nonmetals are always gaining electrons, so they're always going through reduction. Now these guys have to always occur together, because guess what? Those electrons have to go somewhere. You can't lose electrons and then they just float away. They have to go somewhere. Even, if, your battery is, powering something else, those electrons are flowing through your electronic device and then back into the battery to, finally stabilize again. So they're reacting with something, okay, along the way. All right, so here is kind of a little analogy, I think they call it, for remembering that oxidation means the loss of electrons and reduction means the gain of electrons. If you remember the, not phrase, but like the object oil rig, you'll remember that oxidation is loss, oil, oxidation is loss. And reduction is gain, rig, oil rig. Wow, that's amazing. All right, so oxidation is loss and reduction is gain. Okay, so like I said, we're going to go much more depth later in this semester with this, but this is just kind of a heads up as to what an oxidation reduction reaction is. So again, it's either a substance reacting with elemental oxygen, has to be elemental, meaning O2 in the reaction, not like CaO, calcium oxide. That's not elemental, so that's not what we call oxidation reduction. It's got to be O2. Or it is, like we just talked about, metals with nonmetals. All right, or more generally, any substance that transfers electrons to another substance is going through an oxidation reduction reaction. So you peeps that are in AP Bio, right, and you're learning about the Krebs cycle and cellular respiration and photosynthesis. Okay, all of those are all oxidation reduction reactions, because all you're doing is keeping track of where those electrons go. So like turning NAD to NADH, okay, is an oxidation reduction reaction. So they happen a lot in your cells through cellular respiration. That's how we get our energy. Through the transferring of electrons. In fact, remember, there's the electron transport chain, right, that goes on in order to get the hydrogens on the other side of the mitochondria so that they can use that diffusion gradient to slap a phosphate on ATP to make energy. Okay, I'll digress. Anyways, it's found a lot in bio. All right, in combustion reactions is where oxygen is reacting, basically something's reacting with oxygen to form an oxygen-containing compound. So these guys are exothermic because guess what? Fire's hot, guys. Fire is hot. Combustion reactions release their heat in as flames of light and heat. So these guys are exothermic. They're hot. So here, look, this is octane. This is the chemical reaction that occurs in your cars every day that you drive them. So we take C8H18, which is octane. We react it with oxygen in the air. That's why you need an air filter in your car to bring in that oxygen from the air and make sure it's clean. And when you get out your tailpipe, you get out CO2. That's why all of the global warming people hate cars. And water in the gas form. Okay, so it's not like, and actually sometimes you see like water or like a liquid dripping out of somebody's tailpipe. That's just the water condensing back down into liquid. Yep, pretty cool. All right, and here's another reaction. C2H5OH. That's propanol? No, not propanol. Ethanol. Ethanol, and so it's like rubbing alcohol. Not really. Rubbing alcohol is propane. It's ethanol. I'm so done. It is ethanol with oxygen to react again to make carbon dioxide and water. So anytime you burn a carbon compound, you always make carbon dioxide and water. Dun, dun, dun. All right, guys, we come to the last one. We've survived. I hope you have too. I barely have survived. Okay, but this is the last slide. This is kind of exciting. So let's do this. Okay, let me fill in these little arrows first because apparently my computer lost the arrows along the way. The arrows didn't survive this long. All right, so which of the following are redox reactions? Okay, so if you print out your notes, then you'll have these. If not, just pause and try to figure out if A, you're reacting with elemental oxygen, or B, you are reacting a metal with a nonmetal, or C, you just have a transfer of electrons, like you're reducing the charge on something, okay? Because that would be the transfer of electrons. So those three things would classify them as a oxidation reduction reaction. So go ahead and pause and see if you can figure it out. All right, let's see if you did it. Okay, so which ones are redox reactions? Well, first one is magnesium with elemental oxygen. Ding, ding, ding. That's redox. The second one is hydrobromic acid with calcium hydroxide. That is not redox. That is not elemental oxygen reacting. It is has oxygen in it, but it's not elemental oxygen. It is not a pure metal with a pure nonmetal, and we can't basically see that there's any charges that are being reduced. So that is not. In fact, if you notice, it's HBr and CaOH, so this is actually acid-base. Okay, this is acid-base reaction. All right, number 3, calcium, which is a metal, and chlorine, which is a nonmetal, reacts to form calcium chloride. Ding, ding, ding. That is a redox reaction. It's the metal and a nonmetal hooking up. All right, number 4, zinc reacting with Fe2+. Okay, so there's a charge here on Fe. And then in the end, we get zinc with a charge, and Fe has no charge. This, ding, 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 is a redox reaction. It's probably not one that you guessed, though. But you can see that zinc starts off with no charge here and ends up with a charge of 2. So that means he lost. So that means zinc is the oil, right? Oxidation is lost, so zinc is oxidized. And Fe starts off with a 2+ charge, and he goes down to 0. So he gained 2 electrons, so he is reduced, because reduction is gain. Oil rig. Oil rig. All right, let's keep going, because we are almost done. Li plus Cl, metal, nonmetal. Hooking up, ding, 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 oxidation, reduction reaction. All right, carbon with elemental oxygen, making carbon dioxide. Ding, ding, ding. Yes. Redox reaction. Fabulous. Okay. Write a balanced equation for the combustion of liquid methyl alcohol. Okay, let's do that. CH3OH. Okay, combustion means you are always reacting with oxygen, so O2. And remember, anytime you burn something or react something that is carbon-based with oxygen, you always end up with what? That is right, CO2 and water. And of course, you're a good chem student, so you'd balance that equation. I'm not, so we're going to leave it at that because we're done. I will see you next class.